Hadrons and leptons. So there are four fundamental forces that we know of in physics: gravity, electromagnetism, the weak nuclear force and the strong nuclear force. All other forces are just an aggregation of these. For instance, the friction force is just electromagnetism. When you push something, the charges of the particles in your hand electrostatically repel the charges in the object you're pushing. So all forces are one of these four forces. Only charges feel the electromagnetic forces, so neutral particles like neutrons and neutrinos don't feel electromagnetic forces. The type of particles that feel the strong nuclear force are called hadrons. Those are all the particles made of quarks. All particles feel the weak nuclear force, and all particles feel gravity. We can rank the forces by their relative strength. The strong nuclear force is by far the strongest. The electromagnetic force is 100 times less strong. The weak nuclear force is weaker still, and gravity is absolutely puny in comparison with the other forces. They also have different ranges, so the strong nuclear force and the weak nuclear force are very short range, whereas the electromagnetic force and gravity have infinite range. So we can group different particles depending on which forces they can feel. So if we imagine all of the particles of matter and all of the particles of antimatter, we can split them into two groups: hadrons and leptons. Hadrons are the particles that feel the strong nuclear force, and there are two different types of hadron. There's the group of particles that are baryons, that are made of 3 quarks, and the group of particles that are called mesons, that are made of a quark and antiquark pair. Leptons don't feel the strong nuclear force because they're not made of quarks at all. So note that the proton's the only stable baryon. So all other baryons decay into protons. For instance, a neutron on its own will decay into a proton. So neutrons are only stable inside the nucleus with other neutrons and protons. Protons themselves probably have a decay half-life, but it's very, very long. So hadrons feel the strong nuclear force, leptons don't feel the strong nuclear force. Examples of hadrons are protons, neutrons, antiprotons, antineutrons, sigma particles, pions and kaons. Examples of leptons are particles like electrons, positrons, neutrinos, antineutrinos, muons and antimuons. Note that both of these types of particles feel the weak nuclear force. So, as we were saying, hadrons are two different types: baryons and mesons. Examples of the baryons are protons and neutrons and sigma particles, and examples of the mesons are particles called pions and kaons. So in quantum mechanics, we can classify a system by allocating properties numbers, and those numbers are called quantum numbers, and then by thinking about how they change during any interaction. So quantum numbers are the physically important things for the system, and they've got to be conserved. So in any interaction, charge, energy and momentum have to be conserved, but there are also other quantum numbers that have to be conserved. So for instance, for each baryon, we'll give it a baryon number of 1. So a proton has a baryon number of 1, a neutron has a baryon number of 1, and we'll give the antiparticle version a baryon number of -1. So an antiproton has a baryon number of -1, and an antineutron has a baryon number of -1. So in any interaction, the baryon number has to be conserved. Anything that's not a baryon, so it's a meson or a lepton, has a baryon number of 0. So the total baryon number before an interaction has to equal the total baryon number after an interaction. So for example, when a neutron decays, it turns into a proton, an electron, and an antineutrino. The left-hand side is a neutron, it's a baryon, so it has a baryon number of +1. So the baryon numbers on the right-hand side have to add up to be +1. On the right-hand side, we've got a proton, baryon number 1, an electron, and a neutrino that are both leptons, so they have baryon number 0. So we can see that baryon number is conserved, so this decay is possible. +1 equals +1 plus zeros. Mesons are the other type of hadron, so they feel the strong nuclear force, but they are not baryons, so they have baryon number 0. You can get mesons made in particle accelerators and also in high-energy cosmic ray showers in the upper atmosphere. So leptons are a fundamental particle. That means they're not made of any smaller type of particle, and they don't feel the strong nuclear force. They only feel the weak nuclear force, gravity, and if they're charged, the electromagnetic force. Leptons have baryon number 0. But because they're leptons, they do have a lepton number. So for instance, we'll give the electron a lepton number of +1 and an anti-electron, a positron, a lepton number of -1. So just like baryon number, the lepton number before an interaction, the total number of leptons, has got to be the same as the total number of leptons after an interaction. Right. But what makes it slightly more complicated is that there are 3 different flavours of lepton, each associated with a different particular particle. So there's the electron flavour of lepton number, the muon flavour of lepton number, and the tau flavour of lepton number. And we've got to conserve each lepton flavour separately. So for example, an electron has electron lepton number +1, but then 0 for the muon lepton number and the tau lepton number, whereas a muon has 0 for the electron flavoured lepton number, but 1 for the muon flavoured lepton number and 0 for the tau flavoured lepton number. So all particles have the opposite lepton number, and hadrons have lepton number 0. So each flavour of lepton number must be conserved separately. So the total electron flavoured lepton number before has to equal the total electron flavoured lepton number after, and the same for the muon lepton flavour and the tau lepton flavour. So for example, beta- decay. A neutron turns into a proton and emits an electron and an antineutrino. Let's look at the lepton numbers. The neutron is a baryon, it's not a lepton, so it has 0 for every flavour of lepton number. After the decay, we've got a proton. A proton is also a baryon, not a lepton, so it also has 0 for every flavour. The electron is a lepton though, so it's got +1 for its electron flavoured lepton number and 0 for the other flavours. The anti-electron neutrino has -1 for its lepton electron number and 0 for the others. Remember, there are always 3 different flavours of neutrino, and so you can have a neutrino that's electron flavoured, neutron flavoured, muon flavoured, or tau flavoured. So we can see that lepton number is conserved for each different flavour of lepton number. The +1 cancels with the -1 to give 0, and the others are just 0.